All right, today I'm going to be going over the first derivative test as a re-upload, hopefully with fixed audio. So, we're going to first prove some theorems and related concepts. That way we can now create a test for testing intervals of increasing, decreasing, and local extremum. So, first, positive slash negative derivatives imply monotonicity. Now, at a point, if the first derivative is positive, that does not mean necessarily that the function is increasing. It just means that it has quote unquote an upward trend, right? Um, which we've talked about before, but in this case, it does mean the sign of the derivative implies some sort of monotonicity. More specifically, if f is differentiable on the closed interval, or sorry, open interval a comma b and continuous on the closed interval, then if the derivatives are all positive in the interval, then f is increasing, and if all the derivatives are negative, then f is decreasing. Crucially, all of them have to be increasing and decreasing, and it has to be on an interval. Now, why? Well, we're going to prove the first one and the second one is very similar, actually. So we'll let x1 and x2 be in the interval with x1 less than x2. Remember, if we want to prove the function is increasing, we want to show f of x1 is less than f of x2. Now, by the mean value theorem, which we've already proven, there has to be some point c such that the derivative at c is the average rate of change f of x2 minus f of x1 over x2 minus x1. But we know the derivative anywhere is positive, and of course, since x1 is less than x2, x2 minus x1 is positive, so the numerator also has to be positive, meaning f of x1 has to be less than f of x2. And the case again for 2 is similar, and this only works on an interval. And we're going to define now a critical number. We say x naught is a critical number of f if and only if, first, x naught is in the domain of f, and f prime of x naught is equal to 0, or f prime of x naught does not exist, right? Basically, x naught is a critical number if the derivative is 0, or the derivative is not real. And the reason why we're doing this is because we want to find candidates for local extremum. Remember, at a local extreme, either the function is not differentiable or the derivative is 0. So that already helps narrow down tremendously, right? And to determine intervals of increasing or decreasing, we're going to find critical numbers of f, right? All of them. And assuming that f prime is continuous in its domain, right? We're going to assume that f prime is some continuous function, which is most of the functions we're going to be dealing with, if not all. Then we're going to take one test value in each interval between the critical numbers. And the sign of f prime at the test value is the sign of f prime in the whole interval. We only need to check once. And in fact, let's formalize it a bit and prove it. So let a and b be critical numbers of f, and f prime of x is not equal to 0, right? Meaning for all x in a comma b, f prime of x is not 0 and f is continuous. F prime is continuous over a comma b. Then for some x naught in the interval, this is going to be our test value. If f prime of x naught is positive or f prime of x naught is negative, then f prime is positive or f prime is negative respectively over the entire interval. This is what we were just talking about with the test value. Now we're going to assume at x naught, f prime of x naught is positive. Towards a contradiction, we're going to assume that there's some point in the interval, maybe multiple, maybe just one, such that the derivative is not positive there. Now, it cannot be 0 because there are no critical numbers inside the interval, so it has to be negative, right? And either x naught is less than c or x naught is greater than c, but in any case, by the intermediate value theorem, on f prime, there has to be some point x1 in either interval such that the derivative at x1, f prime of x1, is 0, right? Because we have a value, it's continuous, and we have a value where it's positive, a value where it's negative, so it has to be a value where it's 0 somewhere. But this is a contradiction because we said that there are no further critical numbers. So everywhere, if just a single value is positive, everywhere it's positive. And again, the same thing applies for negative, but I'm not going to prove it. So the first derivative test, and this is the theorem, by the way, but the theorem is very simple, but you're going to have to memorize it. Okay, you should know this cold. All right, at least the idea, because on the AP exam, you have to be able to reciprocate it, right? If I ask you to find a local maximum or local minimum, then you have to be able to justify that it is a local maximum because the sign of f prime changes from positive to negative. Okay, so the first part is that if x naught is a critical number of f, and at x naught minus, so to the left of x naught in some delta neighborhood, left delta neighborhood, f prime is positive, and to the right of x naught, f prime is negative, then f has a local maximum at x equals x naught. This is just saying that if x naught is a critical number of f, and f prime changes sign from positive to negative at x naught, f has a local maximum. As well, if x naught is a critical number of f, and at x naught minus, the opposite is true, and at x naught plus, again, the opposite is true, f prime of x is positive, then f has a local minimum at x equals x naught. So whenever we want to justify local maximum or local minimum, we can say that x naught is a local maximum of f because the sign of f prime changes from positive to negative, for example. Or we could say f changes monotonicity, but the AP exam is more looking for the first derivative test justification. So, proof. Now I just explained, actually, believe it or not, what we're looking for, a change in monotonicity, right? If we have a change in monotonicity, we have a local extremum. Um, so we're just going to convert the sign of the derivative to monotonicity, and we already have the theorem for that. So assume at x naught minus, f prime is positive, and at x naught plus, f prime is negative. Then f has to be increasing over our left delta neighborhood and decreasing over the right delta neighborhood. That's the theorem we proved. It was the first one, right? So x naught is a maximum of f over the entire delta neighborhood because, of course, you can verify this if you want, but if f is increasing to the left and decreasing to the right, then at the point it has to reach a maximum. And this is the same thing as saying that f has a local maximum, right? At x equals x naught, right? We could find an interval which contains this point, such that that point is the maximum. So, and of course, 2 is similar, right? Same idea, just flip the sign. And here's our final example. We're going to find the local extremum of f of x is equal to 1/2 x minus sine of x in 0, comma 2 pi. Now, I'm going to walk you through this example. So our first step is always to take the derivative of f, right? Hopefully you know how to take derivatives. In this case, 1/2 minus cosine of x, and evaluate it when it's 0, right? Which is cosine of x is equal to 1/2. And if you know your trigonometry in the interval 0, comma 2 pi, that is pi over 3 and 5 pi over 3. And note, do not forget to check where the derivative is not defined, where the derivative does not exist. In this case, though, it is real for all numbers, but always check where is the denominator 0, and where is the domain of the derivative, right? Where is the function not defined, the derivative. So we're going to build a chart now, right? This is our chart. Hopefully you're looking at it completed, but I'll walk you through it nonetheless. So first, the very first thing we're going to do is we're going to start here, and we are just going to go to erase all of this, right? And I'll walk you through why this works. So first, we're going to take a test values, right? So we've plotted our left and right endpoints, right, given from the problem. If they're not given, it's just negative infinity, positive infinity. Now we're going to draw, right, in the critical numbers, pi over 3 and 5 pi over 3. So crucially, we're going to take test values between each critical number, right? In each interval, we want a test value. And since we know there are no other critical numbers, that sign is going to give us the sign of the derivative in the whole interval, right? So we're going to plug in each test value to the derivative. Notice f prime of pi over 4 is negative, f prime of pi is positive, and f prime of 7 pi over 4 is negative. So we're going to put it's positive here, negative here, and positive. Sorry, the opposite. Negative here. So it's negative here, positive here, negative here. So what does this mean? Well, by the theorem we just proved, right, proved at the beginning, f is decreasing here, f is increasing here, and f is decreasing here. And finally, when we're looking for local max and local min, by the first derivative test, we have a local minimum at x equals pi over 3. because f prime changes sign from negative to positive, which is the same as saying f changes monotonicity from decreasing to increasing. And by the first derivative test, we have a local max at x equals 5 pi over 3 because f prime changes sign from positive to negative there. So you want to be able to say that cold, know that cold, and you will be fine for the AP exam. And this is the first derivative test. So always go back to the fundamentals, even when you have the second derivative test. You can't apply it everywhere. So when you can't apply the second derivative test, which we'll discuss later, apply the first derivative test. Good luck.